Welcome students in the organic chemistry lecture series. In previous three videos we have seen about how to draw the different projection formulas. Like we have seen Fischer projection formula. Then we have seen Newman projection formula, and also we have seen the Sawhorse projection formula. Okay. Now we know that all these projection formulas are used to represent a molecule in two-dimensional space by considering its three-dimensional structure. Now one thing we have to remember is that we can draw Fischer projection formula for a molecule having one stereogenic center also. But to draw Newman projection formula or Sawhorse projection formula, we required a minimum two stereogenic centers. So this is very important. Here also we will require minimum two stereogenic centers. Okay, so we can draw Fischer projection formula for a molecule having only one stereogenic center, and more than that we can draw for 2, 3 also. Okay, but we cannot draw the Newman projection formula or Sawhorse projection formula for a molecule having only one stereogenic center. So this difference you have to represent. Another important thing is that Fischer projection formula represents only eclipse form of molecule. This is very important sentence you remember. Fischer projection formula represents only eclipse form of molecule. Hence, Fischer formula is unsuitable for representing the conformations of molecules. Okay, so we have to convert the molecule into other projection formula. Therefore, a molecule can be represented by any of those projection formula depending upon which aspect of the molecule we have to study. Okay, so these projection formula are interconvertible. All three projection formulas are interconvertible. You remember this thing, interconvertible. Okay, during this interconversion we have to visualize the three-dimensional aspect of the molecule. Then and only then we can understand how to interconvert one projection formula into another projection formula. Okay, the point which we have to keep in mind while interconverting the projection formula are, first thing we have to consider is that how the central carbon-carbon bond is oriented. Okay, so this thing we have to consider, CC bond orientation. This aspect we have to consider while interconverting the formula. Then another point which we have to consider is that the bonds are whether in plane or above the plane or below the plane. Okay, so these things we have to consider while drawing the or while interconverting the projection formula. Also we have to consider it should not affect the stereochemistry at different stereogenic center. Okay, interconversion should not affect the stereochemistry at chiral carbon, we can say, because chiral carbon, stereogenic carbon, both are same. Okay, so these things we have to convert it. Okay, now we have to remember. Now we will move further. Okay, Now, first of all, we will see how to convert a Fischer projection formula into Sawhorse projection formula. To study this conversion, we will take one example. Consider the example of erythro 2,3 dichlorobutane. Okay, so we will draw its Fischer projection formula first. Actually, in examination, the Fischer projection formula is given. Say, for example, the Fischer projection formula of this compound is like this: Cl, Cl, H, H. Now, these chlorine groups are on the same side because you see here this name is here erythro. Erythro means same groups are on same side. Okay, so you see the IUPAC name of this compound, it is 2,3. We'll write here erythro 2,3 dichlorobutane. Okay, so this is the IUPAC name of this compound. Now, while drawing the Fischer projection formula, I have already explained you that the bonds which are on horizontal lines are above the plane and the bonds which are on vertical lines are below the plane. So this structure can be represented like this for our understanding. Okay, now you see here we'll represent this methyl group on the rear side because they are below the plane, and will represent these chlorine groups on upper side because they are on horizontal lines and these atoms are on the above the plane. We have seen this. Okay, so you see this, both hydrogens as well as both chlorine atoms are above the plane, and both the methyl groups are below the plane. Okay, so actually this is the Fischer representation, and we have seen that Fischer projection formula can be drawn for a molecule, and it always represents the eclipse form of the molecule. Now from this Fischer projection formula we have to draw its Sawhorse projection formula. Okay, now while drawing the Sawhorse projection formula, which thing we have to consider? First thing we have to consider is that draw the central carbon-carbon bond at 45-degree angle to the plane of paper. Okay, so we'll draw first. You see here. Okay, so this is the central carbon-carbon bond, which is near about 45-degree to the plane of paper. Okay, now you see here, suppose we are observing the molecule from this end, and this is the first carbon which we observed, suppose this one, and this is the rear carbon. Okay, now you see here on this carbon, this methyl group is on the below the plane. Okay, so we'll write here this methyl group, this is the below the plane. Okay, and these two groups are above the plane, so we'll write these two groups above the plane like this. Okay, it is very simple. You just maintain the stereochemistry, yeah, what is there in the Fischer projection formula. You have to maintain that same stereochemistry in Sawhorse projection formula also. So see this is the first carbon, CS3 group is down the plane, and hydrogen and chlorines are above the plane. Similarly, in the same way we can draw here methyl group, we can draw in the downward side CS3, and these two groups chlorine and hydrogen. Okay, so in this way we can represent the Sawhorse projection of this Fischer. Now this is the eclipse form, we know that. Why is this is eclipse form? Because all the hydrogens, chlorines and CS3 are on same side. Okay, they are near to each other, so this is eclipse form, and this is Sawhorse projection. Sawhorse projection. Okay, now if we rotate this molecule, now suppose this is front carbon, this is rear carbon. Okay, now keep this front carbon same and just rotate this second carbon by 180 degree, we will say. Okay, so 180 degree rotation. You have to fix this carbon and you have to rotate this carbon, or you have to fix this carbon and rotate this carbon. either one carbon atom you have to rotate. Okay, so we are keeping fixed this carbon and we are rotating this carbon. Okay, so first thing we will draw 45-degree angle line. Okay, so this methyl group, it is as it is, CS3, and these two chlorine and hydrogens are also as it is. Okay, now what we are doing, we are rotating this CS3 H and chlorine by 180. So this CS3 will come here, this chlorine will come here, and this hydrogen will come here. So now this CS3 and CS3 will be on opposite side, you see here. So this is now you see this CS3 and this CS3 on opposite side. Okay, now this hydrogen and this hydrogen are on opposite side, and similarly you see here this chlorine and this chlorine on opposite side. So we call this as a staggered form. Staggered form. This is Sawhorse projection. Okay. So in this way we can convert a Fischer projection form into the eclipse form of Sawhorse projection, and then just rotate one carbon atom by 180 degree. You will get the staggered form of that particular Sawhorse projection. So it is very simple to convert a Fischer projection into the Sawhorse projection. Okay. Similarly, we can take 3O23 dichlorobutane example. Suppose this chlorine atom, if we consider this chlorine atom are on opposite side, so we can write like this, and this hydrogen we can write like this. So now what will happen? Stereochemistry will be changed. See, this chlorine will be here, chlorine, okay, and here will be the hydrogen. Here also you have to change the stereochemistry. You see here, now here will be the hydrogen, and here will be the chlorine. Okay, in the same way here also you see here, now the chlorine will be on same side here, and here will be the chlorine, and the name of this will be, instead of 3 erythro, it will be 3O2,3 dichlorobutane. So you might have any structure in front of you, you can convert that into the eclipse form of Sawhorse projection from the Fischer projection formula, and then by rotating one of the carbon atom by 180 degree, you will convert it into the staggered form of Sawhorse projection. Okay, so I think this is very simple and clear to you. In this video we have seen how to convert a Fischer projection formula into Sawhorse projection formula. In next video we will see how to convert a Sawhorse projection formula into Fischer projection formula by taking example. Okay, so thank you, have a nice day, we'll meet in the next video.